Let's see if we can imagine a three-dimensional shape whose base could be viewed as this shaded in region between the graphs of y is equal to f of x and y is equal to g of x. So that's the base of this purple, this I guess mauve or purple color is the base of it. But then it's kind of popping out of our screen. And what I've drawn here in blue, you could view this as kind of the top ridge of the figure. And if you were to take cross sections of the figure, and that's what this yellow line is, if you were to take cross sections of this figure that are vertical, that are I should say perpendicular to the x-axis, those cross sections are going to be isosceles right triangles. So this cross section is going to look like this if you were to flatten it out. So over here it's popping out of your page or out of your screen, but if you were to actually flatten it out, the cross section would look like this. It's going to be an isosceles right triangle where the hypotenuse of the isosceles right triangle sits along the base. So it's isosceles, so that's equal to that. It's a right triangle. And then this distance between that point and this point is the same as the distance between f of x and g of x, for this x value right over there. And obviously that changes as we change our x value. And to help us visualize the shape here, I've kind of drawn a picture of our coordinate plane. If we view it as an angle, if we're kind of above it, and you can kind of start to see how this figure would look. Once again, I've drawn the base. I've drawn the base of it. I've drawn the base of it right over there. And maybe I should, to make it clear, let me make it like this. Let me shade it in kind of parallel to these cross sections. So I've drawn the base right over there. And there's two other sides. There's the side that's on, at least the way I've drawn it here. I guess you could view it as its top side or the left side right over there. And over on this picture, that would be this when we're looking at it from above. And then you have this other side. I guess on this view, this would you could call the right side. And over here, this is kind of when you view it over here, this is the bottom side. So the whole reason why I've set this up and we're attempting to visualize this figure is I want to see if you can come up with a definite integral that describes the volume of this figure that kind of almost looks like a football if you cut it in half, or a rugby ball, but it's skewed a little bit as well. But what's an expression, a definite integral that expresses the volume of this? And I encourage you to use the fact that it intersects at the point, these functions intersect at the point 0, 0, and c comma d. So can you come up with some expression, a definite integral in terms of zeros and c's and d's and f's and g's that describe the volume of this figure? So I'm assuming you've paused the video and have had a go at it. So let's think about it. So if we want to find the volume, one way to think about it is we could approximate the volume as the volume of these individual triangles. So that would be the area of each of these triangles times some very small depth. So let me just shade it in to show the depth. Some very small depth, which we could call dx. So once again, we could find the volume of each of these by finding the area, the cross-sectional area there, and then multiplying that times a little dx, which would give us 3. So this is a little dx, which would give us three-dimensional. That's our dx. I could write that a little bit neater. Dx to give us a little bit of three-dimensional depth. So what is the volume of one of these figures going to look like? Well, if we say, let me just call this height h, and we know that h is going to be f of x minus g of x. That's this distance right over here. So let's call that h. We know that h is going to be, and maybe I should say h of x, because it is going to be a function of x. H of x is going to be f of x minus g of x, But given an h, what is going to be the area of this triangle? Well, this is a 45, 45, 90 triangle. If this is 90, then this is going to have to be 45 degrees. That's going to have to be 45 degrees. And we know that the sides of a 45, 45, 90 triangle are square root of 2 times the hypotenuse. So this is going to be square root of 2, or sorry, square root of 2 over 2 times the hypotenuse. Square root of 2 over 2 times the hypotenuse. And you can get that straight from the Pythagorean theorem. If this side, let's say it's length a, then this side has length a. So you're going to have a squared plus a squared is equal to the hypotenuse squared, or 2a squared is equal to the hypotenuse squared, or that a squared is equal to the hypotenuse squared over 2, or that a is equal to h over the square root of 2, which is the same thing as the square root of 2h over 2. I just rationalized the denominator, multiplied both the numerator and the denominator by square root of 2. So that's where I got this from. And so what is the area going to be? Well, the area is just going to be your base times your height times 1/2. So let me write that down. So the area there, the area is just going to be the base, which is square root of 2 over 2 times our hypotenuse, times the height, which is square root of 2 over 2 times our hypotenuse, times 1/2. Times 1/2. If we didn't do that 1/2, we would be figuring out the area of this entire square. But this is obviously, we're concerned with the triangle. So what's this going to be? This is going to be square root of 2 over 2 times square root of 2 over 2 is going to be 1/2. And then you're going to have another 1/2. So it's 1/4 h squared. Did I do that right? This is, yes, it's going to be 2 over 4, which is 1/2, and then times another 1/2 is 1/4. H squared is the area. Now, what's going to be the volume of each of these triangles? Well, the volume of each of these triangles right over here, the volume is just going to be our area times dx, or it's just going to be 1/4 h squared times our depth, dx. And so if we just integrated a bunch of these from our x equals 0 all the way to x equals c, we essentially have our volume of the entire figure. So how could we write that? So we want to essentially, to find the volume of the figure, and we're kind of in the home stretch here. Actually, let me write it right. Volume, this is volume of a section, volume of a cross section. So what's the volume of the entire thing going to be? Well, the volume of the figure is going to be the definite integral from x equals 0 to x equals c, x equals 0 to c, of 1/4 h squared. 1/4. But we know that h is equal to f of x minus g of x. So instead of h, I'm going to write f of x minus g of x squared dx. And we're done. We just found an expression for, a definite integral expression, I guess you could say, for the volume of this strange figure that we have defined.